We'll see how far we get through this. I'm not sure if we'll make it through all 37 questions or not. We'll see how it goes. So, classic. Okay, nice. Let's get started. Okay, Moore's law states that blank doubles every blank.
This is like day one.
It is
so far back.
final review. So we got everything in here.
Oh, man.
Yeah, so transistors on a chip every 18 months. So it's not necessarily performance. It's just that we have more transistors to do stuff with. It used to be performance. The scale was sort of that every time we added transistors, we could just sort of make the chip go fast. When we double the number of transistors, they go to caches and things like that that maybe double performance for some programs, but not necessarily for everything. So, okay, nice start. Those of you on top. What is a software component of an OS that continuously runs?
That was a trick one.
Trick one. Yes, so kernel with a K, not with the COL. And then system programs are they are there all the time, but they are sort of like LS and CD, things like that. So system components that you need to have, but they're not running the whole time. They're running when someone wants them to. So the kernel is the one that runs constantly. Someone stole your name and is winning? Wow. Okay. True or false? Non-volatile memory loses state when it loses power. Nice, yeah. So non-volatile is keeps its state. Volatile is what loses state. Which storage medium usually has the largest capacity? Okay, nice. Yeah, so main memory is like RAM. Secondary memory would be the storage components. So that's hard disk drives, optical drives, things like that. So hard disk drives generally are the largest in our system. Okay. Next up, which storage medium has the fastest access time of the ones listed here? Nice, yeah. So generally main memory, DRAM is going to be the fastest thing that we have in our system. Non-volatile memory is going to be, things like flash are going to be a little bit slower still these days than DRAM is. Maybe eventually they will replace it, be faster. True or false? Kernel structures can be modified from user space. Okay, So hopefully this has been stomped hard enough this semester. So kernel structures cannot be modified from user space. That's why we need to have things like system calls that switch us from user to kernel mode and then allow us to modify kernel structures. So they are protected in this way from unauthorized access or from accidental access by the user. So we want to make sure that they are not modified from kernel or from user space. Okay. What provides an interface that allows user mode applications to access kernel services? Hopefully everyone was paying attention. Nice, yeah, so system call. System call allows us to cross that boundary from user mode to kernel mode and to access the kernel data structures while we're in kernel mode.
Sir, what's ELF?
ELF, that's the executable linked format for files.
Oh, okay. I remember.
So that's in Linux, yeah.
Gotcha. Forgot about that.
Yep. What type of OS keeps the kernel as small as possible? Nice, yeah, microkernel. So monolithic is the one that sort of pushes everything in the same application in the same kernel. Microkernel has the different services that are linked together with message passing usually. Nice work. And is it a close battle between the two Russians here at the top? Okay. What starts the kernel when the system boots? Yeah, so this is old material, I know. But yeah, the bootloader is the piece of hardware that, or the piece of software that's in firmware usually built into the motherboard that, can find where the OS is and launch the operating system kernel as the computer boots up. Okay. Which part of the memory layout contains global variables? Okay, nice. So yeah, the text segment is sort of code and sometimes constants. The data segment is global variables. The heap is sort of the place that we allocate things with malloc and new. And then the stack is our function variables, local variables usually that get allocated every time we call a function. Okay, next up. Which part of the memory layout contains local variables? Forgot that I had another one of these in here. Yeah, so local variables are on the stack. So the heap is sort of the longer-lived things that we end up allocating to malloc or allocate using malloc or new because they can go over the boundaries of a function call. The stack is for local variables that will sort of be there for our function and then disappear as soon as our function's complete. Okay, next up. Which part of the memory layout starts at a low address and grows toward the maximum address? Okay, got some people. So if we remember, I don't know if I can pull up these notes very quickly. That this would have been from here, I think. Yeah, I can't find it too fast. we have basically the bottom address, so 0 in memory. Going up, we eventually get to the text segment and the data segment, then the heap, and the heap grows up towards the maximum address. The stack starts at a very high address and it grows downward towards the heap. And then if either of those sort of end up hitting each other, we run out of memory. So keep in mind, again, this is the sort of diagram that it's like any way you want to label it is fine as long as you show me where the low address is and where the high address is. And the heap has to be closer to the low address. The stack has to be closer to the high address. It's a tricky question. Man, U5 have a lock on this leaderboard here. It's a tight race at the top. Tough to break in. Okay. What state is a process in when it's waiting for the OS to schedule it on a core? Okay, only got one person. Nice. Sorry to the person I got. So this is the tricky one that when it's waiting to be scheduled, it is in the ready state, right? It's not actually waiting for something. It's just in the ready queue, waiting for the OS to decide that it gets to run. So it is ready to run is what we're saying here. Okay. Next up, what state is a process in when it's waiting for an event to occur? Okay, nice. Everyone got it. Good work. Which of these is not part of the process control block? Okay, yeah. So the rest of the stuff there is part of it. So this is, if we recall, the process control block is the state that we sort of like bring into the process, bring into the core, and then swap out of the core each time we switch processes. So each time we do a context switch, this is the information that we need to do that context switch. So the process state, like whether it's running, ready, waiting, etc., is in there. The process number is in there, so the PID. The registers, so if it is swapped out, it's not currently running, we need a place to store the current or the old register value so that when we context switch in, we can swap those register values in. The cache is the only part that we don't keep in this just because the cache is usually going to be kilobytes or megabytes worth of data, and it's pretty expensive to swap that out and remember the state. And again, the cache is just like a performance optimization on memory accesses. So generally, due to the time scales of how long a process runs versus how long it takes to pull things back into the cache, it's easier to just get rid of the cache state each time we context switch, and then let these things naturally get put back in the cache as the program continues to run. Okay, nice work. So what is the term for a process that is finished but hasn't yet been cleaned up by its parent yet? Okay, yeah, so we had two that we learned about here, orphan and zombie. So zombie is the one that is finished but hasn't been cleaned up yet, and orphan is the one that no longer has a parent. So try to keep in mind orphan, Batman, zombie hasn't been cleaned up. Okay, got a couple lost streaks there. True or false? Processes share memory by default. Yeah, false. So normally processes don't share memory. This is something that we have to enable by mapping or opening a shared file or something like that. Generally, we want to keep processes separate so that they don't interfere with each other. Uh-oh, someone got replaced. Kira's catching up. Okay, which part of the process control block is not shared by all threads? Okay, this is a tricky one. Questions are getting tougher. So all threads are lightweight processes, right? So these are running on different cores is sort of the main point that we need to consider here. But they are running the same code. So each of these threads is going to be, or they're using the same code. They might be running different parts of the code, but the code itself is going to be shared because it's in a same process. The data segments, so like the global variables, things like that, those are still going to be shared, and they have the same memory space as the rest of the threads. So the sort of point here is that threads can share data by default because they're in the same process. And then the list of open files is something that, again, is shared by all of the threads in the same process. These are all process-specific data structures that store open files, and they are shared between the threads. And then finally, registers is the one thing that's not shared because these threads are going to be scheduled possibly to different cores, and so they're going to have their own register values that get sort of split out into the per thread data structures. So it's a tough one. And oh, we have one streak still alive, looks like. So let's continue. True or false? Concurrent applications are not necessarily parallel. Okay, yeah. So we can definitely have a concurrent application that does more than one thing while continuing to use a single core. So these are applications where like we have a background thread while we're waiting for user input. So you know, the user might be or like a website is a concurrent application that's not necessarily parallel. So this is running in one thread, probably on one core. When I click next, it's going to do something. Until I click next, it's, you know, showing this and, you know, can highlight things, and it's sort of waiting for user input while doing things in the background. So that is definitely true. Next up, what is the limit of parallel speedup if 50% of the work can be done in parallel? Do you remember Amdahl's law? Okay, so 2x is correct. So let's pull that up real fast. So Amdahl's law is the speed up is less than or equal to 1 over the serial portion plus 1 minus the serial portion over n, or serial portion plus the parallel portion over n, where, you know, serial plus parallel should add up to 1. So if we are calculating the limit of parallel speedup, as the note here says, we set n equal to infinity, which means that all we have is 1 over the serial portion left. So if we are looking at 50% of the work being done in parallel, that means 50% of the work is done in serial, which means that we have 1 over 0.5 for 2x. Let's see who got it right. Okay, next up, which threading model permits the OS to schedule threads on different cores? Okay. So what threading model permits the OS to schedule threads in different cores? That is one-to-one or many-to-one. So many-to-one, or sorry, many-to-many. Many-to-one is where we have all of the threads being mapped to a single core. Or one-to-one is where we have all threads mapped to different processes, essentially, or different kernel threads. So this is all about how many kernel threads do we have versus how many user threads do we have. And no, she's not playing Valorant or a League. So so one-to-one is that we have one user thread for each kernel thread. Many-to-many is we have some number of user threads to each kernel thread. And the important thing is that kernel threads can be scheduled on different cores. So as long as we have more than one kernel thread or the same number of kernel threads for user threads, we can schedule them on separate cores. If we have many-to-one, then we have multiple threads on the same kernel thread, and that means that we can only schedule those threads to one single core. So we can stop guessing since it'll take you, I think this would have probably taken everyone forever to get to that. So which file system allocation method does not suffer from external fragmentation? So unfortunately, the way I wrote the Kahoot, we're jumping ahead to files, and then we're going to jump backwards to some of the older material from memory management. Which file system allocation method does not suffer from external fragmentations? This is contiguous allocation is the one that does. So keep in mind, external fragmentation is when we sort of have holes of memory left, and we try to allocate something, and we don't have enough space to fill that allocation. So contiguous sort of allocates in big blocks, and then has leftover space that we try to allocate into. Linked and index allocation both allocate single blocks at a time. So we don't end up having external fragmentation there. We might have internal fragmentation where we allocate more than the space that was needed. But in terms of external fragmentation, these two both do not suffer from it, but contiguous allocation does. Oh, Lizard King replaced you again, Kira. Which directory structure allows arbitrary links between files and directories? Let's see. Okay, nice. So yeah, so single level, obviously no links there. Tree structures, you can only link downward. So the key here is arbitrary. We can sort of, have links between different files, but we can't go upward in the graph. An acyclic graph, again, that is not arbitrary because we can only go in a single direction with an acyclic graph. So we have to make sure that things sort of point downward in a graph structure. The general graph allows us to point anywhere in that graph, which means that we can point upward in the graph instead of just downward in the directory structure. So that's sort of the most powerful version of what we looked at. Nice work, 3 in a row, Kai boy. Okay, on this file, what chmod or chmod creates these permissions? Okay, nice. So keep in mind that these are all bits. So each triplet is a set of 3 bits, meaning that R is equal to 4, W is equal to 2, and X is equal to 1. And then we add those up to determine what the number is. So the first one here is 4 plus 2 plus 1 for 7. The second one here is just 4 plus 1 for 5, or yeah, 4 plus 1 for 5. And then the final one is just X, so just 1, which means that it would be chmod 751a.exe. And keeping in mind that we do need the file name after the command to get it to run properly. Nice work. Next up, in which type of locking is the application responsible for manually locking files? Ooh, okay. So mandatory locking is where the OS handles the locking for you. So this is what happens in Windows, where if you have a file open, you can't modify that file. So it's basically essentially like Windows versus Linux. Mandatory is Windows. Blue advisory is going to be Linux based locking. So in Linux, the application sort of handles it for you. So like if you open Emacs and you have a file open already, it'll tell you whether you need to like steal the lock from the other file, or if you need to grab the lock if you're editing it or not. So advisory is sort of the OS will inform the application of the event, saying like someone else is using this already, or someone else is reading this, etc. And then the application can decide what to do from there. Mandatory is that the OS just handles it for you. So yeah, got a lot of people on the leaderboard there. Gollum is making a comeback. Nice work, 3 in a row. Okay, which file access method is inefficient in a system that uses standard linked file allocation? So if we have linked file allocation with no optimizations, what access method is inefficient? Okay, yeah. So in linked allocation, we have sort of a block, a link to the next block, a link to the next block, so on and so forth. So sequential access in that type of system is pretty efficient because we can just sort of follow the links as we sequentially walk through the file. We do have to follow more pointers, which is not great, but it is sort of the most efficient. Direct access, however, we have sort of block, link, link. If we try to access an address somewhere in the middle of that file directly, we have to sort of start from the beginning, follow the links until we've looked at enough data to say that, okay, that's where that piece of data is that we wanted to modify. And same thing for index allocation, where if we have an index, we have to try to find something somewhere in the file based on a key. We're going to have to look through all of the linked blocks to find where that key is going to be stored. So basically anything that tries to jump into the middle of a linked allocation is going to be expensive without optimization. So the optimization on that is usually that we're going to try to add an index or some sort of way to directly access the file there. She's okay. She can say hi if she wants to. I don't know if she's actually in the screen or not. She's not. Here. Dog is trying to say hi to you, everyone. Well, now she doesn't want to be on camera. Okay. Next up, how many 1 GB huge pages can a system with 48-bit addresses support? Okay, nice. So this is essentially a tricky page offset, page number distribution question. So keep in mind that we sort of have, those bits for the page number and the bits for the page offset have to make up the entire number of bits in the address space. So whatever bits are used for addresses, however many bits are used for addresses, that's how many bits we have total. 1 gigabyte huge pages would be 2 to the 30th for the offset. So we need to be able to represent a bit for every byte in the offset. So since we have a gigabyte worth of data, we have to support 2 to the 30th bytes. And that means we have 30 bits for that, which means that we have 48 bits minus 30 bits, leaves us 18 bits left for the page number. And then 2 to the 18th is going to be roughly 256K, or it is 256K. So tricky question, but that is something that might come up on the exam. So see Pancake jump back into the leaderboard. Nice work. How many entries does an inverted page table have in a system with 32-bit address space, 4 kilobyte pages, and 2 gigabytes of RAM? Okay, we might have needed more time for that one. So this is a tricky one too. So the frame table or inverted page table is a frame table essentially, right? So we associate a page number with every frame in the system rather than having a page to frame mapping for every page in the system. So if we had a page table for this, we would have the 32-bit address space divided by the 4 kilobyte pages. So we would have, 2 to the 20th for a megabyte worth or 1 million page table entries. However, in a frame table, we're basically dividing up the 2 gigabytes of RAM by the 4 kilobyte pages. So we'd have 2 to the 31st for 2 gigabytes divided by 4 times 2 to the 10th for 4 kilobytes. And that leaves us with 512K entries in a frame table. So this is the inverted page table. The important thing to remember is the inverted page table keeps an entry for every frame in the system. So we essentially need to know how many frames there are. Okay. Next up, in a 32-bit system with 64 kilobyte pages, what is the page number for address OX123456778? Sorry about the dog noises, by the way. They like to, the big one likes to growl and fight as she falls asleep. So like whenever she feels like taking a nap in the middle of the day, she gets a little noisy. It's a weird habit. Okay, so this is a sort of a tricky one, but easy to hopefully make the connection here. So 64 kilobyte pages, we just need to know what number of bits that is. So 2 to this should be 16th is 64 kilobytes, and that means that that is half of the bits. So it's split into half of the bits for the page number, half of the bits for the page offset, and the page number is the beginning bits, so OX1234. Okay. Ethan jumps back into the leaderboard here. Next up, which allocation scheme leaves behind the most remaining space? Okay, nice. So yeah, so first fit is we find the first hole that fits the allocation we want. Best fit is going to be trying to find the best hole for something, and worst fit is finding the one that has the most remaining space, so we have the most space left to allocate something else. So sort of trying to deal with the external fragmentation problem there. Well, I don't think Phil, have you missed one yet? Nice. Okay. Which allocation scheme leaves the least remaining space behind? Okay, yeah. So best fit is the one that is going to leave the least remaining space. So we're trying to not leave a hole if possible, or leave a small hole because we're assuming that we can't use it then. Okay. True or false, system calls are cheap because they switch from user mode to kernel mode. Right, so system calls are expensive because they switch from user mode to kernel mode. That is not a cheap process to switch over. Which condition is required for a deadlock to occur? Okay, nice. So yeah, so it would be exclusive resources, so things that can't be shared, hold and wait, and then circular wait are the two other conditions. This is one of my ones that makes me giggle, so I decided to keep it for this from earlier in the year. So lack of preemption is the other condition. That's the one that is true. But yeah, hold and wait and circular wait, and then exclusive resources or mutual exclusion. That B looks only like a W. Yeah, it does. Okay. Next up, which deadlock condition can be prevented by a global ordering of resources? Okay, so the global ordering of resources was our solution to the dining philosophers problems. This is where we sort of number each of the chopsticks, and so that way we can make sure that you only acquire them in order of like lowest to highest or something like that for the total number of things you're going to try to acquire. And that prevents the circular weighting, because the problem we have is that, you know, philosopher one grabs the left chopstick, and so basically everyone grabs the chopstick to their left, and no one can grab the chopstick to their right. So if we have a global ordering, then they have to grab sort of 1 and then 2, 2 and then 3, 3 and then 4, 4 and then 5, 1 and then 5, and that 1 and then 5 sort of breaks the ties, because whoever gets the one chopstick first is going to be able to get the next chopstick, or someone will be able to get the other chopstick, because the 1 and 5 will be waiting on 5, or the 1 and 2 will be waiting on 2. So these other conditions, like mutual exclusion, is prevented by like shared resources generally. Hold and wait is that we have some sort of policy where we say, I'm going to acquire all of my stuff at once, and if I can't acquire all of it, I'm going to stop trying to acquire things. And no preemption is obviously we just preempt things, and then we can break the deadlock. It's a tricky one there. Which scheduling algorithm can suffer from the convoy effect? Okay, nice. Yeah, so first come, first served is the one that has the convoy effect. Remember, convoy effect is that we have sort of a large, long-running process that all the short-running processes have to follow. And so if we have sort of a long running, frequently running process, then all of these things that we might want to be responsive have to wait for the long running thing every single time before they get to go. The rest of these, sort of allow these faster processes to run earlier than the long running process, instead of just sort of doing the queue approach where every time it wants to run, it gets to run for as long as it needs to. Okay, 2 more left. Which scheduling algorithms can suffer from starvation? I know you can only answer one, but there is more than one correct answer here. Okay, yeah, so first come, first serve, nope, because it just keeps going through the queue. Eventually, each process gets to run. Shortest job first can suffer from starvation. So if we have a longer job and there are always shorter jobs to run, then the longer job never gets to go. Round robin, we sort of have time quantums that we run each process for a certain time quantum in order. So that's essentially first come, first served, but we only run them for a shorter amount of time. And then priority, obviously, if there's something that has a very high priority versus, or something that has a low priority, it might not get to run because there are always a higher priority process there. It's nice work. Last question. Let's see if Phil can do it. Which condition is not required to implement a critical section? Okay, so yeah, deadlock is the only one of these that is not required. So critical section, we want mutual exclusion, we want progress, we want bounded waiting. So mutual exclusion meaning only one thread gets to go. Progress means some thread eventually gets to go. Bounded waiting, that we have some limit on the amount of time that each thread can wait for. Deadlock is the only thing. Do I validate the exam? Do you need to validate the exam? So no. Let's see. Final podium. So in third place, Fake Phil. In second place, nice work, Groupon. And then first place, perfect score. Nice work, Phil. Okay, so nice work overall. Who are our runners up? Let's just go to the full list here. So nice work, Ethan, and Josh as well. Getting close to the top there. I know we had probably a packed field below that as well. So nice work. Hopefully this jogged your memory a little bit of some of the things that we haven't talked about for a while. And you'll be able to remember to look at those before the exam. So I would say, recommend looking at some of the older material before the exams, that you're familiar with some of the concepts that I might ask about on the earlier parts. It'll probably be just a couple more questions larger than the exam too, just to fill in sort of that 3-hour slot and get to maybe like 150 points, I think. But otherwise, it should be pretty similar and should cover roughly those concepts. So nice work, everyone. I do want to say it's been a pleasure having all of you in class. It's been a little sad that we can't be in person for the past couple weeks, but it's been a fun class to teach. I hope you've enjoyed it. And I will see you on Thursday for the exam. So I will be in Discord and or available via Hangouts if you have questions while we're doing the exam. So, I will be around during that time. But good luck with all your exams, and see you on Thursday.
Thank you, sir.
Thank you, Professor.